Swayam Prabha. Digital India. Educated India.
And the value I like is 120 degrees. Let us talk about a C3 rotation. What is dC3? What is cos theta when theta equal to 120 degrees? And what is sin theta? Root 3 by 2, right? Minus half or plus half? 120 degree? Minus? Sure? Why minus? All sine then, yeah. So this is the matrix, right? There you go. Okay, right? Cos theta sin theta minus sin theta cos theta becomes minus half root 3 by 2 minus root 3 by 2 minus half. That right? Right? What are we transforming? The point, the coordinates of the point. Now let me do it in a little different way. Instead of transforming the point, let me transform the axis. So this is what I want to do. I want to transform the base vectors now instead of transforming the point, and I want to see what kind of matrix we get. And once again, as we will see, the result we get is something that is very much in line with common sense. Alright. So let us proceed. Let us draw something, otherwise it will be a little problematic. What are base vectors? Base vectors are vectors that react with acid vectors. Even vector has some other meaning in biology, right? So what are base vectors? Tell me. X, Y, Z and something more. X, Y, Z are directions, then? Yeah, I heard the right answer. Time. Time is a fourth dimension. Oh no, please do not make things more complicated than they have to be. But I heard the right answer. Yeah, be brave and give me the right answer. X, Y, Z direction is right. What is there other than direction? IJK, yes. What is IJK? Unit vectors, right? IJK is correct. So unit vectors along X, Y and Z, and just to be in the same page as Bishop, we call it E1, E2, E3. So do not get scared, right? E1, E2, E3 is nothing but IJK, right? So let me draw, and here I do not even need E3, because I am working only with X and Y. So let us say these are the base vectors along X and Y, E1 and E2, E1 along X, E2 along Y. What will I do? I will now rotate in clockwise direction by 120 degrees, right? Let me do that, 120 degrees, this is what will be, right? E1 dashed, transformed E1, length is the same, do not forget, even though it does not look the same for some reason, but attribute that to my poor artistic skills. All lengths here are the same, okay, 120 degrees. So angle between E2 and E2 dashed is also 120 degrees. I do not think it is my poor artistic skills, it is the screen is messed up. Perspective is okay, everything is in the plane, so there should be no perspective. The screen ratio has changed in order to be compatible with that. Actually it is looking okay there, on my screen it is looking strange. Anyway, fine. So angle between E2 and E2 dashed is also 120 degrees, right? So we will just write E1 dashed and E2 dashed in terms of E1 and E2, very simple. Okay, in order to do that, just because we are going slow, let us also draw the arrows for minus E1 and minus E2, right, minus E1 minus E2, this is minus E1, this is minus E2, right, right or wrong, that is right transpose, transpose of right. This is minus E1, this is minus E2, not very difficult to understand. Okay. Now, since while we are at it, let us also write down what these angles are. What will this angle be? 60 naturally. How 60? 180 minus 120. Let me ask some easy questions sometimes also. And what is this angle? This angle, man, this is, you are taking it as an insult to your intelligence, and so you are not responding, or what? This is 25 degrees. Then how 30? 120 minus 90, very good. Alright, so everybody is clear about the angles. Now it should be very easy to fill in into this matrix. I want to write it as E1 dashed equal to A into E1 plus B into E2. Okay, how will I do it? Simple vector addition, components should do the trick. All I have to work out is what is the E1 component of E1 dashed, what is the E2 component of E1 dashed, right, and the components will be written here, isn't it? So tell me, what is this length? If I drop a perpendicular from E1 dashed to the E1 matrix, E1 axis, what will it be? Yeah? Louder. Minus half. And if I drop a perpendicular on E2, what will it be? Minus 2 3 by 2. Are we all okay with that? This length, this is 1. So if I drop a perpendicular here, what we learnt in school is that you start with an equilateral triangle and then drop a perpendicular bisector. So if this side is 1, then this side will be half, and since it is half along minus 1 minus E1, it will be minus half, and similarly this will be by Pythagoras theorem root 3 by 2, right. So E1 dashed is equal to minus half E1 minus root 3 by 2 E2, minus half E1 minus root 3 by 2 E2, correct. What is E2 dashed? E2 dashed equal to root 3 by 2 E1 and then minus half E2. Is that right? That right? So this is the matrix that we get, minus half minus root 3 by 2 root 3 by 2 minus half, right. So now see, we have two transformation matrices. One is DC3 associated with transformation of the coordinates, that is minus half root 3 by 2 minus root 3 by 2 minus half, and the other one we get is by transformation of the unit vectors of the base vectors, and that is minus half minus root 3 by 2 root 3 by 2 minus half. Do they have anything to do with each other or not? They are transpose, right. So this matrix that I get by using the unit vectors or base vectors as the basis is the transpose of the transformation matrix that I get when I use the coordinates as the basis. Is that right or is that wrong? It is right, right. Now, okay, so let us write the more difficult thing first and then we will come back to the nicer, easier thing after that. This. So, Kamal, this is what you are talking about? Huh? Let us see if you understand this or not. I am saying Ek dash is equal to sum over j. I do not know why I have written j equal to 1 to 2, I just got carried away by this example. It should be j equal to 1 to n, j equal to 1 to n djk ej. right. What I am doing here is that generally it would be row multiplied by column, but here when I am working with this unit matrix, I can use the same transformation matrix that I get from transformation of coordinates and multiply not by row but by column. That is what gives me sum over j djk ej. What is the meaning of this djk ej? K is constant, right. What is the first subscript, what is the second subscript? First subscript is column, second subscript is row? No. First subscript is row, second subscript is column. So, what we are saying is that we are keeping the column constant and we are going down a column, row number is changing. Is that right? What does this mean? This is my matrix, okay. K is constant, I am summing over j. That means I should go down a column. What is this? D1k, this is D2k, then D3k, so on and so forth, last you have Dnk, right. And what am I multiplying it with? What am I multiplying it with? Ej. So, E1, E2, En. So, this would mean I do not think I have written so much. D1k E1 plus D2k E2 plus D3k E3 plus so on and so forth plus Dnk En. Okay. Why am I doing this? Because the matrix that I am actually multiplying with is the transpose. If this is D, I am actually working with D transpose, right. So, I am actually multiplying by the row, but what I want to do is I still want to keep the matrix that I got from transformation of coordinates and not axes. That is why I am multiplying by column, that is the only. So, first look it might look a little strange, it is not. Do not forget what has happened here. Good that you cannot see it. Do not forget what has happened here. I am working with DC3 prime, not DC3. I am talking about transformation of coordinates. DC3 is the transformation matrix that you get for operation of C3 on the coordinates. When I say coordinates, what do I mean? Position vector, can I say that? Is a position vector that is moving, xyz is changing, that means position vector is going from here to here, right, like this. Okay. Now, we will come back to this, but before that let me write this. DC3 prime is nothing but DC3 minus or DC3 inverse rather. We learned that, right, DC3 inverse. Now, see, does it make sense? What I am saying is the transformation matrix that I get by using the position vector as the basis is inverse of the transformation matrix that I get when I transform the base vectors. What does that mean? And here of course plus minus means clockwise and anti-clockwise rotation, right. Now see, these are my base vectors, okay. This is my position vector. Do you see that clockwise rotation of the position vector is the same as anti-clockwise rotation of the axis, isn't it? That is what it means. Clockwise rotation of the position vector, what it does is it decreases the angle between x and the position vector. Instead, if I rotate the axis, base vectors, then also the same thing happens, right. So, the matrix that I get for clockwise rotation of the position vector should be the same as the matrix that I get for anti-clockwise rotation of the base vector and vice versa. Now, does it make sense, right? This is what it is. That is what we need to remember. If there is a question, please ask now before we go ahead. Two kinds of people do not ask questions, those who have understood everything and those who have understood nothing. So, I assume that everybody has understood everything. Is this notation clear now? Ek dash equal to sum over j 1 to n. I am tempted to change it. Ek dash equal to sum over j equal to 1 to n djk ej, okay. And the most important take home message is that the transformation matrix of position vector and that for the axis, they are just inverse of each other, and here they happen to be transposes of each other, right. So, this is something that we are going to use again. Please do not get confused when I write it in this fashion, because what it implies really is that we are multiplying a column by a column, but do not forget why we are writing it. Do not forget what D is. D denotes the transformation matrix of the point, the coordinates, not the axis, all right. Let us move on. Now, the point is this: we have all these matrices and we know that it is possible by similarity transformation to get diagonalized matrices. So, it should also be possible by similarity transformation to get at least block diagonalized matrices. So, what you could try to do is you take any molecule, use any basis that you want, work out the matrices and then find suitable matrices that will similarly transform these matrices into block diagonalized form and then use the blocks as irreducible representation. Okay. That sounds possible. What are the problems with this? Why do we not want to do this? If you want to do it, of course, we would have gone ahead and done it. If you read Harrison Bartolucci's book, for example, they have worked out how you can block diagonalize the matrices of, I think, C5 group. C5 group. It is worked out. What would be the problem with this? So, that would be okay. What would be the problem of an approach like that? Would there be any problem or are we fine? Yeah? Bigger the matrix, more complicated it will be. Moreover, you cannot just use any matrix to do the similarity transformation, right? We already know which matrix will work. At least one kind of matrix we know already. If it is an n by n matrix, then I think we have convinced ourselves that this eigenvector matrix that we have X that can be used to similarity transform and get diagonalized matrix, completely diagonalized, forget about block. But then that is obviously not the way to go, because what that would mean is that would mean that there is no irreducible representation that is more than one dimensional. Similarity transformation using the X matrix gives you a completely diagonalized matrix, right. So, if that was the way to go, then that would mean that there is no, that means an irreducible representation has to be of dimensionality 1. That sounds a little strange. Besides, when you do a similarity transformation, you should do the same similarity transformation on every matrix, and every matrix is not going to have the same eigenvalues, eigenvector, right. So, just eigenvector matrix will not work. Maybe there is some other matrix like what is worked out in your Harrison-Bertolucci's book. But what is the problem? How do you find the matrix? It is backbreaking. It is like a brute force method, right. Just look at those matrices that are given in Harrison-Bertolucci's book. They are ugly. They actually give you block diagonalized form, but they are ugly. Secondly, the point is, what do I use as a basis? And which molecule do I use? As we discussed earlier, water is C2V, CH2Cl2 is also C2V, right. It is just that the matrices in CH2Cl2 will be double the size of the matrices that we get for water, at least 2 more elements will be there if you only use the atoms. So, using molecule is not a very smart way of doing things. Third point is that question that we asked, that how many irreducible representations are there, that is not answered, because as we see representations depend on the basis, right. What basis you use dictates which representations will show up. It is very possible that there is a representation for which it is not very easy for us to imagine what the basis is going to be. And remember this question, we are going to show you examples of such basis. We are going to show you examples of such representations for which it is not very easy to think of a base. So, that brute force approach is not such a great way of going. So, what we should develop is that we should develop a general theory, something that works for everything, okay. And finally, we should have a machine, a black box into which we will feed any molecule we want, any point group we want, and then this box is going to give us whatever answer it can about that molecule. At least the questions we are asking at this stage, it should be able to tell us how many irreducible representations are there, what are the dimensionalities of those irreducible representations, what are those irreducible representations, okay. If these 3 answers come, that is good enough, we do not need anything more, rest we will see, okay. So, what I am trying to tell you for the last 10 minutes is that just by trying out different combinations of similarity transformation is not a good way to go. We must develop something that is more general, right. So, let us go ahead and do that.